Welcome to the Longhorn session. I'm Shuo, a maintainer from project Longhorn. So I'm also a software engineer in SUSE. So today I'm gonna introduce the project status and then deep dive into some tech detail for you guys. So let's get started. Here is today's agenda. Okay, first let's have a basic overview for this project. So basically, Longhorn is a cloud-native distributed block storage for Kubernetes, and it's always an open resource project, and it's already owned by CNCF for, let's say, over 6 years. And Longhorn, yeah, is a general storage solution. It can be deployed in multiple kinds of environments, including edge case or low spec cluster, on-premises cluster, or public cloud vendors. And yeah, it can adopt to multiple use case as well in AI, telecommunication, data visualization, and observability related issue. Yeah, and it also has pretty good capability with multiple kind of operating systems, not only with traditional OS, but also for immutable OS. Okay, so right now, in the past years, Longhorn always keep a pretty good adoption in the community. We have solid growth in both Git stars and active node usage all over the world. And in the recent year, our release cadence become more and more stable. Right now, we have 4 months feature release cadence and 2 months patch release cadence. And internally, we also have a 2-week sprint release since we are using Agile developing. And our latest feature release is 1.10 in this September. And since the release cadence is pretty quick, so we also have a bunch of comprehensive quality assurance mechanism, including regular end-to-end test and negative test case. Those are all automated. And besides, for every release, we will scan the CVE issues and update the BCI image to guarantee all critical CVE issues are resolved in the latest version. And in the daily development, our QA will do lots of manual verification for each issues, tickets, or improvement. That's really solidate our release quality and project quality. Okay, then let's talk more about the tech detail for this project. So first, there are 3 main design principles in Longhorn system. First, reliability. That's the most important thing for the storage solution. So since Longhorn is a block storage solution, so we will follow the crash consistency with a bunch of data protection mechanisms. We will introduce this later. And second, usability. Actually, this is one highlight of Longhorn system compared with other kind of solution. We have pretty easy on-click installation via kubectl, Helm, or Rancher. We have polished user experience with a pretty, let's say, easy to use UI there. We also have a comprehensive documentation in our website. And the last, the maintainability. Since Longhorn architecture is relatively straightforward and simple, it's easy to understand and to maintain for cluster admin or for the cluster manager. And it's also and it's also easy to recover the data even in the worst case scenario happens. I mean, even if the whole cluster or even if the whole node is down, if you can get the disk, you can easily recover the data with the script we provide. And based on the principle, here is the control plane architecture. So, for example, if a workload pod, let's say a database, requests persistent storage from Kubernetes, Kubernetes will send the container storage interface API to the upper Longhorn CSI plugin. Then this plugin will forward the request to Longhorn Manager, which is an orchestrator between Kubernetes and Longhorn internal resource. Then this Longhorn Manager will ask the underlying component to, let's say, provision one engine and a bunch of replicas on multiple nodes for each volume. Then that's the basic architecture in the control plane. It's pretty straightforward. Then let's go deeply into the data plane. So let's say there is an application using Longhorn volume for persistent storage. So typically it may, let's say, make a file system on top of it first. But this is not necessary in Longhorn, so we don't care this part. Then for the IOs from application or from the file system will be forwarding to this block device, which is actually an SCSI initiator provisioned by Longhorn. Then all IO requests will be forwarded from this block device to Longhorn TGD, then to the underneath Longhorn engine via the customized protocol. Then once this Longhorn engine is actually a process only, and once this engine receives a read or write request, they will forward the request to the corresponding replica. For the read request, it will fetch a random replica to handle it. For the write, since Longhorn volume is a crash consistent volume, so we will apply synchronized write to all replications for each request and wait for all replica response, then return the result to the upper layer. So basically, it's latency sensitive, and there is no cache inside it. And with this architecture, Longhorn achieved a bunch of capabilities. So we have full support with Kubernetes along with CSI protocols. We have a lot of kind of storage topology that fits your cluster's scenario or current state. And for Longhorn volume, it has multiple capabilities, not only related to the block storage layer, we also support file system train and expansion. And based on that, we have a bunch of data protection and data service, including replication, encryption, bit rot detection, and snapshot backup and disaster recovery. We will introduce some features in the upcoming pages. So first, volume snapshot. This is the basic design or data architecture in Longhorn system. Let's say for the right part is user or applications perspective. So it's like a raw block device list in the right part. So, but in the left part is the internal view of a volume replica. So first, it just had a volume head sparse file. So the left for the left, that list is actually a sparse file. When users write some data blocks into a Longhorn volume, then each replica will record it in its current volume head file. And then later on, if the user want to create a snapshot, then in Longhorn's perspective, we just rename the previous volume head file to the snapshot and mark it as immutable, then create a new volume head file. So this there's no data copy involved, so this is an instant operation, almost no I/O suspension. And right now, if user want to write more data, including an overlapping part, then for Longhorn, it will record everything in the new volume head file. So for the overlapped data in the snapshot one, it won't be erased or really, let's say, recovered. It's like a pen only design. So later on, if something is wrong with the current volume head, users still have a chance to revert to snapshot one without any data loss. And that's the basic idea of design of long volume snapshot is pretty straightforward. Then, based on this snapshot design, Longhorn can deliver the corresponding incremental backup feature. So let's say at this moment we want to do the backup for the current snapshot 1. So we will figure out the corresponding data blocks and upload the data blocks onto the remote backup target. And then more data is written into this volume and will be recorded in the current volume head. And at this moment, if user want to create one more backup, then Longhorn will automatically create a corresponding snapshot first, which is snapshot 2, then backup this snapshot. So as you can see, backing up snapshot 2 means we need to back up 3 active blocks, but one of the block is already inside this remote backup target and is pointed by the previous backup. So we don't need to do the repeat data transfer at this moment. Instead, we just need to, let's say, upload the new data blocks only. This is what we call the incremental backup. Then for the corresponding deletion, it's pretty straightforward. If we want to delete the backup of snapshot 2, we just need to remove the corresponding meta file along with the data blocks only belong to it. For the shared data blocks, it won't be affected. Yeah, and then for the restore, that's pretty straightforward as well. We just need to copy the corresponding data blocks from the remote backup back to a new volume head. That's it. And based on this backup design, Longhorn can deliver a pretty advanced cross-cluster disaster recovery feature. Let's say we have a primary cluster which runs our current application and service, and there's application service using Longhorn volume for the data storage. First, we can deploy a remote backup target that will periodically back up the latest data for the corresponding volumes. And then we can launch another, let's say, secondary or disaster recovery cluster, maybe in another data center for the backup, and create a special volume named disaster recovery volume that periodically monitor and fetch the latest data from the backup volume. So here, both the primary and DR cluster are pointing to the same remote backup target. Later on, if there are more data generated in the primary cluster, then we can do incremental backup, as we mentioned before. Then later on, the DR volume will monitor the change in the corresponding backup volume and fetch the latest data only. If there are more volumes, we can create more backup and then create more DR volumes coordinating. And let's say at one moment, the primary cluster is done. Then users can quickly activate the DR volume in the DR cluster and, let's say, recover all application and service on top of it. This greatly reduces the service downtime, or we call it RTO or RPO. So for the actual time reduced, it depends on the, let's say, backup interval as well as the DR volume check interval. And that's the basic feature set and data protection mechanism Longhorn delivered. Then we will talk a little bit more about the V2 data engine in our Longhorn project. So basically, this is a next generation data engine based on SPDK. It's achieve high I/O performance for Longhorn volumes. So SPDK by default use pooling mode with dedicated CPU and dedicated huge page to speed up the I/O. But basically, in Longhorn, the architecture are pretty similar, as we can see in this V2 data plane architecture illustration. So there are only several changes comparing with V1. So first is the front end previously we use iSCSI. Right now we use NVMe over Fabric protocol. And previously we are using Longhorn own engine or replica processor to, let's say, forward the corresponding data. Right now, we will rely on SPDK to do that. And the last difference is that previously Longhorn replica process rely on the host file system. But here, SPDK require a dedicated raw block storage. This can greatly reduce some kind of intermediate operations and context switch and data copies. Then it can greatly speed up the I/O. And then we will rely on this kind of environment to do some benchmark and see how powerful V2 data engine is. Notice that this is a pretty powerful cluster. It's using an NVMe disk, so it's let's say raw block device. Its raw block device IOPS is near 1 million per second. So for V1, it has a volume. It has a pretty obvious bottleneck here. But for V2, as long as you can provide enough CPUs, then it can achieve almost half of the baseline and 11 times of V1 volume in read IOPS perspective. And for the write, it's similar. So for V2, it can achieve almost 1/3 of the baseline, 8 times of V1. And for the throughput, things are better for both V1 and V2. So because it's involved not too much about the latency. Then for the latency, yeah, due to the dedicated CPUs, pooling mode, and dedicated raw block device handled by SPDK, it can greatly reduce the latency in the whole I/O path. As you can see, for the local replica case, it's just less than 2 times of the best time in the latency perspective, and half of the V1 volume. For the 3 replica case, things are still similar, 3 times of the baseline, 2/3 of V1 volume. And for the write, same. Since write is synchronized write, so it's a little bit worse comparing with the read. But we can also achieve, for the V2, we can also achieve, let's say, 4 times of the baseline, 1/3 of the V1 volume in the local replica case. And here's actually one more benchmark we did during the V2 POC. As you can see, for the same amount IOPS, V2 data engine consumes much less CPU and RAMs. The only exception in this chart is in the bandwidth related benchmark along with the RAM, because V2 require dedicated huge pages. Here we provide 1 GB huge page, but this single volume benchmark cannot fully utilize that 1 GB huge page. Then in this chart, the RAM's consumption per megabyte looks a little bit higher, but I think it's acceptable. And finally, we will talk about the latest feature and upcoming feature release details. So in the most recent release 1.10, we delivered a bunch of V2 related features, not only for the regular improvement like rebuilding related, but also some kind of new features. For example, for this right now, V2 volume support both full clone and linked clone. Linked clone is actually an instant clone for the volume. With this new feature, it can cooperate with Valero and then deliver a general backup solution. So if you guys are interested, you can check the latest blog post in our website, which tell you how to do that. And besides, we also enabled interrupt mode and support for running without huge pages for V1 volumes. This means in the future, Longhorn is this V2 volume can be can fit into the low spec environment. And besides V2 related feature, we also have a bunch of improvement for the general features. So I won't mention and list it one by one here. And then for the feature planet in the upcoming 1.11 and 1.12, still we will do more. We will implement more features for V2 data engine, but we also focus on the polishment of V1 volume user experience, along with multiple kind of resource related control and monitoring mechanism. Okay, last, community. So if you guys are interested in Longhorn, you can discuss issue or questions in our GitHub page or in CNCF or Longhorn in Longhorn Slack channel. And in this in our website community page, we have a monthly meetup calendar there, so you can join if you are interested. And besides, if you already tried Longhorn, or if you feel okay, the user experience is good in Longhorn, then you can share your use case in this documentation and submit the PR. So any use case are welcomed. And if in the future, if you want to do more, let's say contribute to Longhorn in any of the area listed, you can check the corresponding repos in our Longhorn GitHub. And if a new contributor and not familiar with the tech details, you can use good first issue. You can use this label to filter the corresponding issues. So periodically, our Longhorn maintainer will, let's say, filter out some kind of relatively easy project for the new contributors. And I think that's it. So if you guys have any questions, so you can go to the middle of the room. There is a microphone stand here. Then we can, then I can answer your question. Oh, thank you.
Hi, thanks for the whoa, man, that was louder than I expected it to be. So I see a lot of similarities in your growth path and discovery path moving towards the V2 engine that I saw with the Ceph project. Have y'all looked at the Ceph project and seen some of their pitfalls and used that as their lessons learned and taking that as a takeaway to improve your platform before reinventing the wheel there?
Sorry, the microphone is vague since.
So are you familiar with the Ceph project?
Sorry?
Ceph?
Yeah.
Okay, so Ceph's path from file store to Blue Store really mirrors a lot of what I saw from your V1 to V2 backend. Have y'all looked at what Ceph discovered along their path and journey in providing software-defined storage to help you in your development of this product? I guess the answer is no.
Yeah. Okay. So let's back to this. Yeah, for the Ceph, yeah, I haven't looked into it for, let's say, for already for a period of time. So, but basically, what to say?
No, it's okay. Oh, absolutely. It's all, if you go to Ceph.io and look at their migration, there's like an 18-page paper on just their initial discovery with file store and what their discoveries were in doing that method and why they went to developing their own file system for their backend in their migration to Blue Store. And I just see a lot of similarities in that discovery path with the development of Longhorn. And as those things progress, there's some new tooling like NVMe over Fabric that I think is really cool and would have been fantastic for the Ceph project early on, but just didn't exist at the time. So you're able to take advantage of some newer technology that wasn't available to them while they were in their cycle of discovery and development. And it's kind of interesting to see the similarities between those two. But thank you.
Yeah, thank you.
Hi there. Oop, is that working? Yeah, that's a little better. First off, excellent switch to NVMe over Fabrics, and wondered if you'll take advantage of RDMA in situations where you can use it.
Sorry. Weird.
Am I being too quiet?
Uh-huh.
Are you taking advantage of remote DMA in your
Remote RDMA, right? Yeah, for
correct.
that one, it's not a general solution. I mean, actually, a lot of cluster does not have the specific, let's say, hardware or design. So at this moment, we still mainly focus on the over TCP protocol.
Great.
Yeah, but I did some time to investigate it. So maybe we will support it in the future. But to be honest, it's currently not in our roadmap. Yeah, I know that one is pretty powerful.
Yeah, it can help get you the last little bit of latency out of the transaction.
Yeah.
And the other question was about the data plane v2 and whether that's a sort of a standard server process that I can add to a Debian system so that I can export, say, I don't know, a stack of onboard NVMe disks to a Longhorn engine that can then consume that and break it up with some mechanism like LVM to to export these volumes.
To export what?
Well, I was wondering if you're using something that's a generic server or for the disk side of the transaction, the persistent side, or if that's something that's necessary to be in the Kubernetes cluster. Use daemon set to manage the hardware, right? And then is that process that you're running in the daemon set something that I can just like app install on a Debian server and have a little collection of disk servers in my VPC that I then get Longhorn volumes off of? You know what I mean?
You mean?
I want to treat like a bunch of storage, a bunch of instances with local storage as a storage array.
Yes. So then, so you want to treat those kind of as storage? Then what's the question?
Well, the question is, can I run this as an independent process on the Debian host? Or does it have to be part of the cluster?
You mean run outside of Kubernetes?
Outside of Kubernetes.
Currently, no. To be honest, but everything is based on container. You can do it manually, but in that case, I don't think it's involved too much about Longhorn itself, because Longhorn just directly use SPDK. But if in that case, if you can, let's say, execute a container by yourself and group those storage as engine or RAID 1, based on SPDK, actually it's similar like Longhorn, but you just do it manually. So yeah, but anyway,
So,
Longhorn cannot run outside of Kubernetes.
So in typical deployment scenarios, so you'd have maybe a node group that had local disk on board that would run that daemon set, and then that would service all the engines that you have in the cluster. Is that the case?
Sorry, daemon set.
Yeah, I mean, presumably there's a daemon set that talks to the raw block devices and exports the SPDK target, right? So that runs on instances that have local storage to be exported, correct? And so then those aren't necessarily the same type of instances that you're running your application on. You probably want big apps with no local, or big nodes with no local disk.
Yeah, then no local disk should be fine, because the engine
uses the network to.
Yeah.
And so then you would have, like, in an EKS cluster, you have two different node groups. You have a node group for your applications and a node group for your disks. Right?
Yeah.
Yeah, so that's a common deployment scenario.
Yeah.
That envision with this, and I'm just trying to get my head around it, and yeah,
Yeah, so Longhorn does not, let's say, block this kind of usage as well. So you can mix your application storage together, or you can have dedicated storage nodes or disk. So both are supported. I don't think there are any question or blocker in Longhorn usage. So
cool.
yeah, basically, I mean, starting from V1, our one basic principle is that we can utilize as much as possible with existing resources on cluster nodes to deliver the storage. For example, for V1, we can directly use the, let's say, root file system available space to provide the storage.
Yeah,
Or yeah, you can.
You can also use NVMe on board.
Yeah.
Now that you're using NVMe over TCP,
Uh-huh.
the latency characteristics are better.
Yeah.
You can really get some strength in, like database acceptable performance out of it.
Yeah. That's why we switch from iSCSI to NVMe due to this kind of latency or more advanced architecture design.
Hey, how many snapshots can you support?
Snapshot by design is 250, but we highly recommend to create too many snapshots. As you know, snapshot will record historic data, right? It will, let's say, consume much extra space. Let's say you just create a volume with 100 gigabytes spec size, right? Which means each snapshot can eat up to 100 megabytes, gigabytes space at most. That would be crazy if you create too many snapshots. Then I did saw some users complaining about the space usage after creating too many snapshots, but without a periodic cleanup. Then based on this kind of use case, we also have a bunch of restriction configurable regarding to the snapshot size and snapshot count.
Is there an operator that can flatten them periodically?
Yeah, there is a recurring job that can do multiple kind of things, periodic backup creation, backup deletion, and periodic snapshot creation, deletion, cleanup, and even the recurring file system trim. Yeah.
So you can shrink the file system down.
Yeah. Because basically, at the beginning, Longhorn is just a block storage, but there are indeed a lot of use case along with file system, and file system trim can indeed reduce a lot of disk usage pressure. Then finally, we decide to deliver that feature. But it's mainly happened in the CSI layer. I mean, we have in the control plane architecture, we have let's say a CSI plugin which implements CSI interface. In that layer, we will do some kind of file system related operations. Yeah. Yeah. Thanks. I guess the session is over. Maybe for you, we can discuss it offline.
Yeah, that's all. Another quick question on: are there any improvements planned for the read-write mini feature?
Oh,
particularly around NFS Ganesha stability.
You mean stability or
stability?
Oh, okay.
Like with latency, I've noticed in some clusters that I've managed that NFS Ganesha will actually completely lock up if there's high disk IO.
Oh.
And you have to restart the whole system.
Okay, I got it. Actually, so you are mainly focused on the read-write many volume improvement. Yeah. So in the recent release, we are still focused on the HA read-write many, which means if the underneath, as you know, when we create a read-write many volume in Longhorn, actually there will be a corresponding Ganesha NFS server inside. It's called Share Manager in Longhorn, and in the recent release, we are focusing on how to recover it within a shorter period of time. And as for the, let's say, latency rate improvement, I'm thinking if we can, let's say, integrate this Ganesha server along with V2 instead, because right now we will assume read-write many is running on top of V1.
Right.
along with just along with the NFS. But yeah, we will see if there can be any kind of improvement with V2.
Okay.
Yeah.
Gotcha. So that could be a feature coming out. Okay, cool.
Yeah.
Thank you.
Thank you.
Yeah, I have a question.
Mhm.
So my question is, we currently have a operate a stretch cluster across 2 data centers,
Mhm.
and the data is not copied over; it's created in Bentley.
Uh-huh.
Is it possible to have 2 Longhorn engines, one at each data center? So
Are they in the same Kubernetes cluster?
yes,
It's considered in the same Kubernetes cluster, right?
yes.
So, yeah.
Because for data replication here,
Mhm.
we would have nodes 1, 2, 3 in
Mhm.
data center 1, and 4, 5, 6 in data center number 2.
Mhm.
But I don't want the data replicated across all nodes.
Yeah, you can easily do that by, let's say, assign the corresponding tag and selector.
Okay.
Yeah, for the nodes on this data center, you can use the same tag, and then when you create a corresponding volume, you can have the corresponding selector. So
And it's all using